Welcome to today's paper reading. Today's paper is titled Concise Thoughts: Impact of Output Length on LLM Reasoning and Cost. This paper, authored by Sania Nayab and colleagues from the Department of Excellence in Robotics and AI at Scuola Superiore Sant'Anna, examines the impact of output length on large language models, LLMs, and proposes metrics to evaluate conciseness and correctness. The work is currently under review. This paper addresses the efficiency of large language models, LLMs, in generating detailed reasoning outputs. It analyzes how the length of model outputs affects inference pipelines and introduces new metrics to assess correct conciseness. The authors propose a refined prompt engineering strategy called Constrained-CoT, CCoT, which aims to control and limit the output length of the model. Experimental results on pre-trained LLMs show that CCoT not only improves accuracy but also reduces the average output length. For example, constraining the reasoning of Llama 2-70B to 100 words increases accuracy on the GSM-8K dataset from 36.01% to 41.07%, while cutting the average output length by 28 words. The introduction of this paper discusses the advancements in large language models, LLMs, and their application in complex question-answering tasks. Specifically, the paper highlights the effectiveness of chain-of-thought (CoT) prompting and enhancing the correctness of model outputs. However, it also points out that CoT can lead to longer response times due to the nature of autoregressive transformers. This issue is particularly problematic in interactive settings where quick responses are necessary. To address these challenges, the paper proposes new metrics to evaluate the conciseness of model outputs and introduces a novel prompting strategy called Constrained-CoT, CCoT. This strategy aims to limit the length of reasoning while maintaining accuracy. The paper also presents experimental results demonstrating the impact of CCoT on various LLMs, showing improvements in both accuracy and response times for certain models. Recent works on large language models, LLMs, have primarily focused on enhancing their accuracy. However, as these models scale up, they tend to produce more extensive and articulated responses, which can lead to issues such as hallucinations and unnecessarily long explanations. To address these challenges, prompt engineering has been introduced, involving the strategic design of input patterns to guide models toward more accurate responses. Despite these efforts, the output length often increases due to the additional context provided. Another notable approach is chain-of-thought prompting, which requires models to provide step-by-step explanations alongside final responses, though this often results in lengthy outputs. This work aims to address these issues by proposing novel metrics that consider both conciseness and correctness, as well as a revised version of chain-of-thought prompting to control reasoning length. The generation time of a large language model, LLM, is influenced by several factors, including the model's architecture, pre- and post-processing steps, and the use of prompt engineering techniques. In an encoder-decoder architecture, such as that used by transformers, the generation time increases with the number of output tokens due to the repeated invocation of the decoder. Additionally, the chain-of-thought (CoT) method, while improving the correctness of responses, significantly increases both the output length and the generation time, highlighting the need for a balance between accuracy and efficiency. Figure 1 illustrates the relationship between the response time and the output length for 3 different large language models, LLMs, across various tasks. The tasks include summarization, question answering, QA, context and then QA, and topic modeling, using samples from datasets such as CNN/Daily News, Squad Combination, FELM, and AG. The plot clearly shows that as the output length increases, the response time also increases significantly for each LLM. This indicates that the length of the output has a direct impact on the generation time of the models, which is crucial for understanding the efficiency and practicality of using LLMs in real-world applications. Figure 2 analyzes the impact of chain-of-thought, CoT, on the efficiency of the Falcon 40B model. Part A shows the relationship between response time and output length, comparing performance without CoT, blue dots, and with CoT, red dots, across 100 questions from the GSM-8K test set. Part B illustrates the variation in output words between conditions with and without CoT, using 50 random samples from the GSM-8K test set. This section introduces 3 novel metrics to evaluate the capability of an LLM to provide both correct and concise responses. These metrics redefine the classic accuracy metric to integrate conciseness aspects into the correctness of LLM outputs. The first metric, hard K concise accuracy, HCA-K, measures the fraction of correct outputs that do not exceed a specified length K, promoting strict length constraints. The second metric, soft K concise accuracy, SCA-K, alpha, generalizes HCA by penalizing longer correct answers exponentially with a decay factor alpha, allowing for some tolerance. The third metric, consistent concise accuracy, CCA-K, alpha beta, further generalizes by also accounting for the variation in output lengths, promoting consistency in response lengths. These metrics are designed to be particularly useful in scenarios requiring strict length adherence or consistency, such as real-time systems or environments with limited computational resources. The authors introduce a method called Constrained Chain of Thoughts, CCoT, prompting to enhance the efficiency of chain of thoughts, CoT, while maintaining accuracy. This approach aims to balance the trade-off between efficiency and accuracy by introducing an explicit constraint on the output length. The CCoT prompt is structured as x equals concat, thus xp xl, where xp requests reasoning steps and xl specifies the output length constraint. An example demonstrates that while a CoT prompt generates an answer of 67 words, a CCoT prompt with a 45-word constraint generates a correct answer in just 34 words, illustrating improved conciseness. Figure 3 demonstrates the application of Constrained Chain of Thoughts, CCoT, in a zero-shot setting using a question from the GSM-8K dataset. The top box illustrates the traditional chain of thoughts, CoT, approach, which produces a detailed reasoning process totaling 67 words. In contrast, the bottom box showcases the CCoT method, which constrains the output length to 45 words, resulting in a concise yet correct answer of 34 words. The figure highlights the effectiveness of CCoT in reducing output length without compromising the accuracy of the response. The experiments were conducted using the text generation inference platform on 8 NVIDIA A100 GPUs, evaluating 5 pre-trained large language models from Hugging Face on the GSM-8K test set, which includes 1.3K mathematical problems. The primary focus was to assess the impact of the CCoT approach on computation time and accuracy. Results indicate that CCoT significantly reduces generation time across various models while maintaining or improving accuracy. Additionally, CCoT demonstrates the ability to control output length effectively, though smaller constraints pose challenges. These findings highlight the benefits of CCoT in balancing efficiency and correctness in language model outputs. Figure 4 presents the generation time and accuracy of 5 LLMs on the GSM-8K test dataset. The models are evaluated using plain prompt, base, CoT, and CCoT with various length constraints. Notably, CCoT significantly reduces generation time across most models, particularly for Llama 2-70B, where the time nearly halves with a 15-word constraint. In terms of accuracy, Llama 2-70B and Vicuna 13B show improvements with CCoT, reaching up to 41.77% with a 100-word constraint. Conversely, Falcon 7B, the smallest model, faces challenges with large CCoT constraints, resulting in lower accuracy compared to CoT and base. Figure 5 illustrates the distribution of output lengths between the 5th and 95th percentiles for various models and prompting strategies using the GSM-8K test set. The models analyzed include Vicuna 13B, Falcon 40B, and Llama 2-70B, each tested with different prompt strategies such as base, CoT, and CCoT. The box plots in the figure represent the output lengths, with the blue line indicating the provided CCoT length constraint, the red line denoting the median, and the green dot representing the mean. This visualization helps in understanding how well the models adhere to the imposed length constraints under different prompting conditions. Figure 6 presents the hard K concise accuracy, HCA, scores for Llama 2-70B and Falcon 40B across various values of K, infinity, 100, 80, 60, and 40, and different prompting methods, base, CoT, CCoT. The bar plots in A and B illustrate the performance index achieved by each model under the specified conditions. Notably, the application of CCoT prompting shows a beneficial effect on the model's ability to produce correct answers within the given length constraints, especially for less stringent limits. This suggests that CCoT enhances the model's performance when the length constraint is not overly restrictive. Figure 7 presents a comparison of soft conciseness accuracy, SCA, scores for Llama 2-70B and Falcon 40B models using different prompting methods, base, chain of thought, CoT, and constrained chain of thought, CCoTs. The scores are evaluated with two tolerance values for accepting longer answers, alpha equals 1 and alpha equals 10. This figure helps in understanding how different prompting strategies affect the conciseness and accuracy of model outputs under varying length constraints. The study highlights the significance of addressing the conciseness of answers generated by LLMs in text-to-text tasks. It introduces the constrained chain of thought, CCoT, method to control output length. The impact of CCoT on generation time and response correctness was evaluated using question-answer benchmarks. The findings indicate that smaller models like Falcon 7B, Llama 2-7B, and Vicuna 13B struggle with length constraints, whereas larger models such as Falcon 40B and Llama 2-70B exhibit better control. Factors such as the training dataset and parameter count influence this performance. Future work will delve deeper into understanding these issues and explore integrating the proposed metrics into the fine-tuning process. Thank you for watching.